Welcome to another lecture. Today, let us discuss the Space Shuttle Challenger disaster, a topic that is at once technical, historical, and deeply human. I am Alexei, and we shall proceed carefully and precisely.
Hello, I'm Priyanka, Professor Alexei's teaching assistant. I hope we can think about this together with care and with clarity.
Let's begin with the foundations. The Challenger disaster refers to the in-flight breakup of Space Shuttle Challenger 73 seconds after liftoff in January 1986, with the loss of all 7 crew members. In simpler terms, what should have been a routine, well-rehearsed climb to orbit suffered a catastrophic seal failure. Imagine a bicycle where a tiny split in an inner tube is ignored because previous slow leaks always seem to hold. And then, at the highest speed and bumpiest pavement, the tube ruptures. In rocketry, margins can vanish in milliseconds when small defects meet peak aerodynamic stress. A few essential terms. SRB stands for Solid Rocket Booster. 2 large solid propellant boosters flanked the external tank and supplied the majority of thrust at liftoff. An O-ring is a circular elastomer seal meant to keep high-pressure, high-temperature gases contained. In each SRB field joint, there were 2 O-rings intended to function as primary and secondary seals. Max Q denotes maximum dynamic pressure, the point in ascent where aerodynamic loads on the vehicle are greatest. It is crucial to understand that seals which are marginal at ignition are most likely to fail as the stack passes through max Q.
Professor, may I ask something simple first? So, was it basically the case that the O-rings just did not move fast enough to seal when everything pressurized at liftoff, and then max Q made a small leak become a fatal one?
Fundamentally, yes. In record cold conditions, the rubber lost resiliency, so seating was delayed. Early blow-by occurred. Molten aluminum oxide likely formed a temporary plug, and then wind shear and peak loads at max Q broke that fragile seal. Hot gases burned through the right SRB joint and impinged on the external tank, after which structural failure and rapid propellant mixing precipitated breakup. That is to say, a chain of events with no realistic opportunity for crew intervention unfolded in seconds. Why this matters? The disaster reshaped NASA's policies, the nation's confidence in human spaceflight, and our understanding of organizational risk. After Challenger, crewed launches paused for 32 months. Commercial satellite deployments shifted to expendable rockets. An Office of Safety, Reliability, and Quality Assurance was created. SRB joints were redesigned, and crews thereafter wore pressurized suits for ascent and re-entry. Public perception moved from a narrative of routine access to space to a sober recognition that mature programs can harbor latent hazards if dissenting engineering voices are discounted.
I think the stakes are also cultural. When organizations treat recurring near misses as normal, we, learn the wrong lesson. It makes me wonder how quickly such drift can happen under schedule pressure. 2 basic facts to anchor us. First, millions watched the launch live, including many schoolchildren, because of Krista McAuliffe and the Teacher in Space program, which amplified the national impact. Second, it was the first fatal accident involving an American spacecraft in flight. Previous US astronaut fatalities, like Apollo 1, were on the ground.
Now, 2 chronological points that establish pattern. O-ring erosion and blow-by were documented as early as 1981, and by 1985, erosion occurred on nearly every flight, in one case affecting both primary and secondary O-rings. Then, on the evening before the launch in January 1986, engineers at Morton Thiokol, notably Roger Boisjolet and colleagues, warned that the forecast cold threatened O-ring sealing. Management initially recommended no launch, then reversed after an internal caucus, and a go was conveyed. Alan MacDonald declined to sign at the pad. NASA manager Lawrence Malloy required formal concurrence. Mission management lead Arnold Aldrich was not told the full temperature debate. We observe a sequence in which known vulnerabilities met a launch decision process primed to proceed. Before we get to the complexities, a brief personal note. I was a young student in Russia when Challenger launched. Our teacher wheeled a television into the classroom, which for us was rare and exciting. The image of the plume blooming against the Florida sky and the sudden silence in the room imprinted the idea that engineering is not merely calculation, it is also conscience. That morning sent me, as it were, down a lifelong path toward understanding how systems fail and how we might do better. Moving forward, we will consider three large questions, one historical, one counterfactual, and one still open. Priyanka, would you pose the first?
Professor, what were the key factors that led to management's decision to proceed with the launch, despite warnings?
Several factors converged. There was cumulative schedule pressure. January had already seen delays cascading from earlier missions. Public attention was heightened by the Teacher in Space program. Late-night news even mocked the previous day's stuck hatch bolt as, quote, high-tech low comedy, which, while trivial technically, shaped optics. Inside NASA and its contractor, years of non-catastrophic O-ring erosion had normalized deviance. By 1982, the supposed redundancy was reclassified to criticality 1, meaning failure could be fatal with no reliable backup. Yet launches continued while a redesign lagged. On the evening before the launch, Thiokol engineers argued they lacked data showing safe performance at the forecast cold temperatures. In response, management reframed the burden to prove it unsafe. After an internal caucus, the company reversed to a launch recommendation. Joe Kilminster signed. Alan MacDonald refused. Lawrence Malloy accepted the go. Arnold Aldrich was not fully briefed on the O-ring debate. And the launch commit criteria did not include SRB joint temperature, so the cold did not automatically trigger a no-go. Mathematically, one might say qualitative judgment substituted for missing cold data, but in the wrong direction.
Professor Alexei, could you clarify how these pressures influence the final decision? Like, how did culture translate into a yes at the pad?
Of course, we can infer two mechanisms. First, managerial framing. The standard became effectively launch unless conclusively unsafe, rather than do not launch unless conclusively safe, which is a subtle but profound inversion when data are sparse. Second, normalization of deviance. Repeated erosions without loss conditioned leaders to treat symptom as acceptable variance. The engineer's caution was recast as over-conservatism under the weight of schedule and public optics. In this context, dissent did not escalate cleanly. Voices like Roger Boisjolet's and Alan MacDonald's were documented but not decisive. The Rogers Commission later criticized precisely this decision dynamic.
What if NASA had delayed the launch to wait for warmer conditions, Professor?
If the launch had waited for temperatures within the engineer's comfort band, the O-rings would likely have sealed promptly. Previous colder-than-normal flights in 1985 showed erosion but not failure, implying a temperature sensitivity with a threshold that January 1986 probably crossed. Under warmer conditions, the right SRB joint may not have leaked. No plume would have eroded the external tank. The mission might have deployed the TDRS-B satellite and conducted Halley's Comet observations as planned. The immediate consequences would plausibly include preserved schedule momentum and public confidence. However, it is worth noting that the underlying design vulnerability would have persisted until the redesigned joints flew. Absent a dramatic wake-up call, organizational reforms may have arrived later or more slowly. Counterfactuals are instructive but not proofs. In this case, the available evidence supports a materially safer outcome in warmer weather, though not a solved root cause.
Professor Alexei, could this decision have changed the trajectory of human spaceflight? I mean, would we have seen a different pace or even different uses of the shuttle?
Potentially, yes, at least in the near term. A successful STS-51L might have sustained a higher launch cadence for a time, and perhaps delayed the policy shift that moved routine satellite deployment to expendable rockets. Yet the Columbia Accident Investigation Board in 2003 later concluded that NASA did not fully internalize Challenger's organizational lessons. That suggests cultural issues can remain latent even across successes. In simpler terms, avoiding one catastrophe in 1986 could have preserved schedule and trust, but absent structural changes, risk would have continued to accumulate in other forms. Spaceflight, like chess, punishes optimism bias. A temporarily successful gambit does not render a weak square strong.
Professor, what do we still not know about the crew's final moments?
Two categories of evidence and one limit. We know several personal egress air packs were activated, and some lever-locked cockpit switches were found moved. Neither the breakup nor ocean impact can account for those positions, implying purposeful human action after structural separation. We also know the crew cabin descended ballistically and impacted the ocean at forces far beyond survivability. The limit is pressurization. Dr. Joseph Kerwin's report concluded that we cannot determine whether the cabin lost pressure before impact. The PEEPs provided unpressurized air and were not designed for ascent emergencies. In conclusion, some crew members were almost certainly conscious for part of the descent. The exact physiological timeline remains indeterminate, and the lack of an ascent escape system rendered the outcome inevitable once the cabin separated.
Is there ongoing research into understanding these uncertainties, Professor Alexei?
To some extent, yes, but the emphasis today is forward-looking. Forensic study of recovered artifacts continues as new debris is occasionally found, such as a large fragment identified in 2022 off Florida, which is respectfully secured with the rest at Cape Canaveral. More importantly, the safety community has focused on design and procedural mitigations. Redesigned SRB joints with captured seals and limited rotation, ascent and re-entry pressure suits, refined hazard communication, independent safety oversight. The open questions about the final minutes motivate, not morbid speculation, but the imperative to ensure no future crew faces the same constraints. To summarize, Challenger broke apart 73 seconds after liftoff because a right SRB field joint failed to seal. Cold impaired O-ring resiliency. Temporary sealing delayed but did not prevent burn-through. And aerodynamic and structural loads completed the chain to catastrophic breakup. We examined three questions: how decision-making under schedule and cultural pressure normalized the known hazard, what a weather delay might have changed, and what remains unresolved about the crew's final moments. For comparative lessons, consider studying the Space Shuttle Columbia disaster. The through lines in organizational communication are regrettably instructive.
So, I guess that kind of sums it up. Thank you, Professor.
This concludes our lecture for today. Thank you for listening. Read widely, question assumptions, and as it were, mind the seals.